In this video I'm looking at the noise, sideband noise added by 1 nanofarad capacitors at 10 megahertz. Here is a ceramic capacitor. I have tuned it in parallel to 10 megahertz to make the transmission from input here to output with low attenuation. It's loaded by the losses of this LC resonant circuit. And this is what I see on the network analyzer. The loss is 1 dB and the impedance is close to 37 ohms. So there is a small mismatch which will probably not affect the noise figure of the test system. I'm using the same setup as in the previous video, this one. So look there if you want to have the details. And clearly there is some noise produced in this capacitor. I have to reduce the signal level a little bit. Well, here it is nearly stable, 1 dB more. Well, here it's fairly stable. So I read the noise floor. I have to wait until it moves like that. And I see 0.7 dB. That's with an attenuator setting of can't see this. What does it say? 6 and 0. And the signal level then is 0.5 dBm. And I haven't changed anything. It is now more noisy. So I reduce again the level. So maybe this would be more fair for this component. I wait a little while to see what happens. So now I see a noise signal at 1.6 dB, and that is with an attenuator setting of 10 dB here plus 5 dB here, 15 dB. For a signal level of minus 8.7. I have put the information into this Excel spreadsheet, reading 1.6 dB noise increase, and this is the power I see on the spectrum analyzer, the attenuator setting. And here is the power in linear power scale. The noise increment, 1.6 dB, is a factor of 1.445. And then the noise from the capacitor is 0.445, because 1 comes from the low noise amplifier. And I can convert this to dBm per hertz with this formula. And the power from the coupler, the power actually coming out from the test object is like this, 20.05 dB stronger. Knowing the power as well as the noise power density, I can compute the noise modulation in dBc per hertz, like that. And then I can measure the voltage. I know that the load is 50 ohms, so I can compute the voltage across the capacitor like this. And from the voltage I can compute the current. But I have to change that formula. The impedance of 1 nanofarad at 10 megahertz is 15.9 ohms. So the current has to be about 52 milliamps at this point where the noise is a little bit increased. This is a polypropylene capacitor. The capacitance is a little bit larger, so I had to change the coil a little bit. The losses are much lower. On the resonance it's only 0.1 dB, so the impedance is very close to 47 to 50 ohms. There is no attenuation. They're both set to 0. And the noise is very low, like this, 0.33 dB. So I compare it with the straight-through wire, because it is now one day after I calibrated things. But as you can see, the straight-through wire is very similar. So it means this capacitor does not add any noise, or at least very little. So if I read this out from the straight-through wire, it says 0.28. So this difference of 0.05 dB may be statistical uncertainties. I can do, well, I clear screen again and look at the capacitor and the straight-through wire, and then there's a difference of 0.05 dB, which means that the noise is far below the minus 205 dBc per hertz. That is the limitation of this test system. The level on the coupler is 7.9 dBm. This is a polycarbonate capacitor. I didn't change the coil, but the tuning seems to be the same as for the polypropylene. These plastic foil capacitors come with fairly high precision. I have set 0 attenuation, and the power then is 7.6 dBm. And the noise is significantly larger than for the polypropylene, but it looks nice and stable, and it's 1.66 dB. This is a paper capacitor from Rifa, rated 630 volts. The losses are significantly higher than the plastic foil capacitors. I lose 1.6 dB here, and the impedance is only 34 ohms. I'm running it now without any attenuation, and that gives a signal level of 6.7 dBm. And there is a significant amount of noise the noise increment is 4.2 dB. I now add some attenuation, 1 dB, 1 more dB, 1 more, and again 1 dB. And I take the readings that I get here. That is with 4 dB of attenuation and a signal level 2.0 dBm. And the noise increment is 1.46. So this is regular in the way how it adds noise, while ceramic capacitors typically are unstable. So with 4 dB attenuator setting, I get a very similar result for the added sideband noise. This is probably within the accuracy of the measurements I do. I'm running now with 10 dB of attenuation, and I switch to 0 now. And look at what happens to the noise. And I wait a little. It's quite clear that the noise increases with time. Not so surprising, the losses are high, so this capacitor is heated. There is 300 milliamps through it, and well, the loss is, I have forgotten, was it 1 dB or even more, and the power level here is about half a watt, so 1 dB loss of half a watt, that gives a significant amount of heat. This is a 4 kilovolt Mica capacitor. Losses are fairly low. I see 0.2 dB through. I have set no attenuation, and then the signal level is 7.7 dBm. The noise floor looks stable, and it is at 0.33 dB, so this doesn't add any noise. Here is a ceramic disc capacitor rated 400 volts. It's an old one from some surplus that I have found. It looks like this, a little bit more lossy than the plastic foil, but it's still reasonably good. There is no attenuation, and then the signal level is 7.5 dBm. The noise floor is stable at a level of 0.34 dB. And I can see there are some problems with the local oscillator, but because of the very deep notch, it doesn't affect these measurements. This is a Mica capacitor. It's one of these, and on the other side I can see the manufacturer, and it says 500 volts working voltage, made in USA. The losses are fairly low, so the impedance is very close to 50 ohms. The noise level was here initially, but after a not long time it has went down to this value that I see here. Well, don't see it. Yes, I do. So it is 0.46 now, or 0.5. But it was a little bit higher at the beginning. Something has become heated or rearranged it inside this capacitor. But occasionally there are some noise bursts, but at low levels. So I rate this capacitor at 0.5. Well, that was unfair. I have just been waiting a little more, and here we had some bursts of noise. So I think I will take this region in time and say it's 0.95 dB instead. The power is 7.8 dBm, and that's for an attenuator setting of 0 on both sides. Here is a Mica capacitor from TCC, and it looks like this, so the losses are low here. The noise you can see here, that's when I put the lid in place. I mean, screening the box from the noise from my computers and stuff here. And the level I had without the lid, 0.37, and with the lid, 0.33. And I measured everything with the lid in place, of course. And the power I see is 7.8 dBm. And of course that's with no attenuator settings, 0 and 0. I have now moved the connectors to the straight through wire to see what is the noise floor of the system that I have. And what I see is 0.30. And here are the results, and they are all very good. With the straight through wire, the system limit is minus 206. So when I measure 205, the noise of the capacitor is far below this value. There is one Mica that has some noise, but still it's below minus 200 dBc per hertz. It's nothing to complain about. The paper capacitors gives a little noise, not much. The small ceramic, that gives a significant amount of noise, although it's minus 180, so nobody would worry about it, I think. And that's at a current of 50 milliamps. The other capacitors are measured at 300 milliamps of current at 10 megahertz. So I found nothing interesting in this study, I think.